What does a major subduction zone earthquake actually look like when hundreds of kilometers of rock suddenly move? How much energy must be stored beneath the seafloor before an entire region begins shaking at once? And what can new footage from southern Mindanao teach us about the geological forces that have been building beneath the Philippines for centuries? The new videos emerging from southern Mindanao following the magnitude 7.8 earthquake near Cablalan offer far more than dramatic scenes of shaking buildings and swaying ground. For geologists, seismologists, and earth science enthusiasts, the footage provides a rare real-world demonstration of how energy accumulated deep within the earth is released in a matter of seconds. Every oscillating structure, every rolling ground motion, and every prolonged vibration visible in the recordings represents the surface expression of enormous tectonic forces operating tens of kilometers beneath the Philippine region. The earthquake struck at approximately 26 kilometers southwest of Cablalan in southern Mindanao, at a depth of roughly 55 kilometers beneath the surface. Initial analyses indicate that the event occurred within one of the most tectonically active regions on Earth, an area where the interaction between multiple tectonic plates continuously reshapes the crust. The earthquake generated severe shaking across large portions of Mindanao and was followed almost immediately by a sequence of powerful aftershocks, including events measuring magnitude 6.5, 6.1, 6.0, and several others above magnitude 5. The rapid succession of significant aftershocks highlights the enormous stress redistribution that followed the main rupture. To understand why this earthquake became so powerful, it is necessary to look beneath the islands of the Philippines and into the structure of the Earth's lithosphere. The Philippine region sits within an extraordinarily complex tectonic environment. Unlike many parts of the world that are dominated by interactions between only two major plates, the Philippines occupies a zone where several plates and microplates converge. This convergence creates multiple trenches, fault systems, and deformation zones. South of Mindanao lies a major subduction system associated with the Philippine Trench and the broader tectonic interactions involving the Philippine Sea Plate and surrounding crustal blocks. In a subduction zone, one tectonic plate is forced downward beneath another and gradually descends into the mantle. This process occurs at rates that may seem slow from a human perspective, often only a few centimeters per year, yet over decades and centuries, enormous amounts of elastic strain accumulate. The process can be imagined as a gigantic geological spring. As the plates continue moving, friction prevents smooth sliding along portions of the plate boundary. Instead, the rocks become locked together. Despite appearing solid and immovable, rocks at these depths are subjected to immense pressure and can deform elastically. Energy gradually accumulates within the surrounding crust. Eventually, the stress exceeds the strength of the locked zone. When that threshold is crossed, rupture begins. The stored elastic energy is released almost instantaneously relative to geological timescales. The rocks rebound toward a less stressed configuration, generating seismic waves that radiate outward through the earth. This mechanism, known as elastic rebound theory, remains the fundamental explanation for large tectonic earthquakes. The moment tensor solutions released for the earthquake indicate a predominantly compressional faulting mechanism consistent with subduction-related deformation. The rupture geometry suggests significant vertical and horizontal motion associated with convergence between tectonic blocks. The high percentage of double-couple energy observed in the seismic solution indicates that the earthquake was primarily driven by fault movement rather than more complex deformation processes. One of the most fascinating aspects of the event is its depth. Although the hypocenter was reported at approximately 55 kilometers, some seismic solutions place the principal rupture closer to 35 kilometers. Either way, the earthquake occurred well beneath the shallow crust, but still within the seismically active portion of the descending slab. Depth plays a major role in determining how shaking is experienced at the surface. A very shallow earthquake often produces extreme localized damage because the seismic waves have little distance over which to lose energy. A deeper earthquake, however, can spread its energy across a much broader region. The seismic waves travel through large volumes of crust before reaching the surface, allowing shaking to be felt over vast areas. This helps explain why millions of people experienced noticeable ground motion during the event. The earthquake's magnitude and depth combined to produce widespread shaking throughout southern Philippines and neighboring regions. Shake map estimates indicate severe shaking reached intensity levels capable of producing substantial structural damage in vulnerable buildings. The newly released footage provides valuable clues regarding the nature of the seismic waves involved. Many videos show a prolonged rolling motion rather than abrupt jolts. This characteristic is important because different types of seismic waves arrive at different times and produce different motions. The first waves generated during an earthquake are primary waves, commonly called P waves. These compressional waves move by alternately squeezing and expanding the material through which they travel. Because they travel fastest, they are usually the first indication that an earthquake has occurred. Following the P waves come secondary waves, or S waves. These waves move material perpendicular to the direction of travel and generally produce stronger shaking. Because S waves cannot travel through liquids, they provide important information about Earth's internal structure. After the body waves arrive, surface waves often dominate the motion experienced by people. Surface waves travel along the Earth's exterior and can produce large horizontal and vertical displacements. In major earthquakes, these waves frequently cause the most visible movement. The swaying observed in many videos likely reflects the arrival and persistence of surface wave energy. Large earthquakes generate long-period waves capable of moving entire structures back and forth. Buildings, bridges, towers, and even groups of people may appear to move in unison as the ground oscillates beneath them. Magnitude 7.8 earthquakes are capable of generating extraordinary amounts of energy. Although earthquake magnitudes are commonly discussed as though they increase linearly, the scale is logarithmic. Each increase of one whole magnitude unit corresponds to approximately 32 times more energy release. Consequently, a magnitude 7.8 earthquake releases vastly more energy than a magnitude 6.8 event and hundreds of times more energy than many earthquakes people commonly experience. The total seismic moment associated with this earthquake was estimated at approximately 5.7 times 10 to the 20th Newton meters. That value reflects the enormous volume of rock involved in the rupture and the amount of displacement that occurred along the fault surface. Another important clue comes from the aftershock sequence. Within minutes of the main earthquake, several powerful aftershocks occurred throughout the region. These were not separate random events. Instead, they represent the crust adjusting to a dramatically altered stress field. Before the main shock, tectonic stress was distributed across numerous faults and rock volumes. When the major rupture occurred, that balance changed suddenly. Some areas experienced stress relief, while others experienced stress increases. Faults pushed closer to failure may rupture shortly afterward, producing aftershocks. The sequence recorded after the Cablalan earthquake illustrates this process remarkably well. Multiple events exceeding magnitude 6 occurred within a short period, indicating that the regional fault network was actively responding to the redistribution of stress. For Earth scientists, aftershocks provide a unique window into the geometry of the rupture zone. By mapping their locations, researchers can estimate the dimensions of the fault segment that failed during the main earthquake. The spatial pattern of aftershocks may also reveal whether rupture propagated along the plate interface, extended into the overriding crust, or involved structures within the descending slab itself. This question is particularly important in Mindanao because the region has experienced numerous large earthquakes throughout recorded history. The historical record demonstrates that southern Philippines repeatedly generates major seismic events. The magnitude 8.3 earthquake of 1918, the magnitude 7.9 earthquake of 1913, the devastating magnitude 7.9 Morro Gulf earthquake of 1976, and the magnitude 7.8 earthquake of 1936 all testify to the immense tectonic potential of the region. These events occurred in different parts of the broader southern Philippine tectonic system, but collectively demonstrate a long history of large-scale strain release. The 1976 Morro Gulf earthquake remains particularly relevant when examining the geological significance of the current event. That earthquake generated a destructive tsunami and highlighted the hazards associated with major offshore fault movement. Large subduction earthquakes can produce vertical displacement of the sea floor. When significant portions of the ocean floor are suddenly lifted or lowered, the overlying water column is displaced. That displacement initiates tsunami waves. Unlike ordinary wind-driven waves, tsunami waves involve movement throughout the entire water column. Their wavelengths can extend for hundreds of kilometers, allowing them to travel across ocean basins with relatively little energy loss. Whether a particular earthquake generates a large tsunami depends on several factors, including fault geometry, rupture direction, vertical displacement, water depth, and total rupture area. The Mindanao earthquake triggered tsunami warnings because its magnitude and tectonic setting suggested the possibility of significant seafloor deformation. Initial forecasts indicated potentially hazardous wave activity in portions of the Philippines and neighboring countries. From a geological perspective, one of the most interesting questions concerns exactly where within the subduction system the rupture occurred. Subduction zones contain several distinct environments capable of generating earthquakes. Some earthquakes occur directly on the plate interface where the descending and overriding plates meet. These are known as megathrust earthquakes and represent some of the largest earthquakes on Earth. Others occur within the descending slab itself. As the slab bends, compresses, and sinks into the mantle, stresses develop within the plate. These stresses can trigger large intraslab earthquakes at intermediate depths. The depth and focal mechanism of the Mindanao event suggests that researchers will carefully examine whether the rupture occurred on the plate boundary itself or within the descending slab. Determining the answer will help refine models of stress accumulation throughout the region. The footage also highlights another important geological principle. Local ground conditions strongly influence earthquake shaking. Not all locations experience identical motion during a major earthquake. Seismic waves interact with different rock and sediment types as they travel. Hard bedrock generally transmits waves differently than unconsolidated sediments. Soft sediments can amplify shaking, particularly for certain wave frequencies. This phenomenon, known as site amplification, helps explain why neighboring communities sometimes report very different levels of damage despite being similar distances from the epicenter. Sedimentary basins can also trap seismic energy, causing waves to reverberate and prolong shaking. In urban areas built atop thick sedimentary deposits, ground motion may continue significantly longer than in nearby regions underlain by bedrock. Many of the dramatic motions visible in earthquake videos result from the interaction between incoming seismic waves and local geological conditions. Another lesson emerging from the earthquake concerns rupture duration. Large earthquakes do not occur as a single instantaneous event. Once rupture begins, it propagates along the fault surface at speeds that can approach several kilometers per second. The fault progressively breaks over a large area. For a magnitude 7.8 earthquake, rupture may continue for tens of seconds. During that interval, different segments of the fault release energy, generating complex wave patterns that arrive at the surface over extended periods. The duration of shaking often contributes significantly to structural damage. Buildings can withstand brief forces more easily than prolonged oscillations. When shaking continues for many seconds, repeated loading and unloading cycles place increasing stress on structural components. The videos from Mindanao reveal this prolonged character clearly. Rather than a brief jolt, many locations experience sustained movement consistent with a large rupture involving a substantial fault area. The earthquake also offers scientists an opportunity to study stress transfer throughout the Philippine tectonic network. Large earthquakes rarely occur in complete isolation. Each rupture changes the stress distribution across surrounding faults. Some faults become less likely to fail immediately, while others move closer to their failure threshold. Researchers use Coulomb stress modeling to estimate how earthquakes influence neighboring structures. Such analyses can reveal whether future seismic activity may become more likely in adjacent portions of the tectonic system. The numerous strong aftershocks already recorded demonstrate that stress transfer is actively occurring throughout the region. For science enthusiasts watching the footage, perhaps the most remarkable realization is that all of the visible motion originated from processes occurring far below human observation. No camera captured the fault itself moving. No observer watched the rupture propagate through the crust. Yet every swaying building, every rippling roadway, and every oscillating object represents evidence of deep geological processes operating beneath Mindanao. The videos transform abstract tectonic concepts into observable reality. They show that plate tectonics is not merely a theory describing continents moving over millions of years. It is an active process occurring continuously beneath our feet. Most of the time, that movement is too slow to notice. Occasionally, however, centuries of accumulated strain are released in less than a minute. That is what happened near Cablalan. The magnitude 7.8 earthquake was the product of long-term tectonic convergence, stress accumulation, fault locking, elastic deformation, rupture initiation, seismic wave propagation, and regional stress redistribution. The subsequent aftershock sequence reflects the crust's attempt to establish a new mechanical equilibrium. As scientists continue analyzing seismic records, GPS measurements, satellite observations, and aftershock patterns, the geological story of this earthquake will become clearer. Researchers will determine the precise rupture dimensions, identify the fault plane involved, estimate slip distribution, and refine models of the southern Philippine subduction environment. The footage now circulating across the world serves as the visible record of that event. Beyond the dramatic images lies a powerful scientific lesson. The shaking seen on screen was the surface expression of tectonic forces that have been accumulating for decades beneath one of the most active plate boundaries on Earth. For a brief moment, the hidden mechanics of our dynamic planet became visible, revealing the immense energy stored within the Earth's crust, and reminding us that the geological engine driving the Philippines remains very much alive. The sequence of aftershocks that followed the magnitude 7.8 earthquake provides another important opportunity to understand how large tectonic systems behave after a major rupture. To many observers, the strongest event appears to be the end of the story. From a geological perspective, however, the main shock often marks the beginning of a new phase in the evolution of the stress field. The earthquakes measuring magnitude 6.5, 6.1, 6.0, and several additional events above magnitude 5 occurred within a relatively short period after the main rupture. Such activity is typical following a major earthquake because the crust surrounding the rupture zone has been abruptly forced into a new mechanical state. Before the main shock, stress was distributed across a network of faults and rock volumes throughout the region. Once the fault slipped, that balance changed almost instantly. Imagine a tightly compressed system of interconnected springs. Releasing one spring does not necessarily bring the entire system into equilibrium. Instead, the motion can transfer forces to neighboring springs, causing additional movement elsewhere. Fault systems behave in a similar manner. Stress that had accumulated over decades or centuries may be released on one fault segment while simultaneously increasing stress on adjacent structures. This redistribution of stress helps explain why aftershocks can occur across a surprisingly broad area. The locations of these earthquakes are not random. Seismologists carefully map every aftershock because the pattern often reveals the geometry of the fault that ruptured during the main event. Clusters of aftershocks frequently outline portions of the fault plane that experience significant slip or identify neighboring structures responding to the stress changes. Another fascinating aspect of the Mindanao earthquake involves the depth distribution of the aftershocks. The sequence ranges from roughly 35 kilometers to more than 70 kilometers beneath the surface. Such depths place many of these events within or near the descending slab of oceanic lithosphere. This observation may provide clues about the internal stresses acting within the subducting plate itself. As oceanic lithosphere descends into the mantle, it does not behave as a perfectly rigid block. The slab bends, stretches, compresses, and undergoes changes in temperature and pressure. These processes generate complex stress patterns capable of producing earthquakes at various depths. In some cases, large earthquakes occurring within the slab can trigger additional failures in nearby portions of the descending plate. Researchers will likely pay close attention to whether the aftershock distribution follows the geometry of the subducting slab. If it does, The sequence could provide valuable information about how stress is transferred through the interior of the descending plate following a major rupture. The event also highlights an important concept often overlooked in public discussions of earthquakes. Magnitude alone does not tell the entire story. Two earthquakes with identical magnitudes can produce very different effects depending on depth, rupture direction, local geology, and the frequencies of seismic waves generated during fault movement. One factor scientists will examine is rupture directivity. Earthquake ruptures do not always spread uniformly in every direction. Sometimes the rupture propagates preferentially along a particular segment of the fault. When seismic energy is focused in the direction of rupture propagation, shaking can become significantly stronger in regions located ahead of the advancing rupture front. This phenomenon is similar to the way sound waves can become concentrated in front of a moving source. In large earthquakes, rupture directivity can influence both the intensity and duration of shaking experienced at the surface. Detailed analysis of seismic records collected throughout the Philippines may reveal whether directivity played a role in the distribution of observed ground motion during this event. Ultimately, the magnitude 7.8 Mindanao earthquake serves as a reminder that the Philippine archipelago exists within one of the most active tectonic environments on the planet. The forces responsible for this earthquake did not emerge suddenly. They are part of an ongoing process driven by plate convergence, subduction, deformation, and stress accumulation operating continuously beneath the region. The newly released footage captures only a few moments of that process, but for Earth scientists, those moments offer a remarkable glimpse into the powerful geological mechanisms that continue to shape the Philippine landscape today.